we are now looking at the integral of sine of ln of x, right? And what I was asking is, what substitution do you think we can use there in terms of integration by parts? So what would you suggest as a substitution? So what is our u and what is our dv? Any suggestions? Any suggestions? Come on, guys. What do you think? I'm sure you have ideas. Feel free to share them with the group, you know.
Can we make u equal to ln x, because ln x it is easy to differentiate it than to integrate
Oh,
it.
thank you. Thank you. That's a very good preposition. So thank you for that. So we would let our u be equal to ln x, right? Easy function to differentiate. And therefore, that would mean that our dv now, right? Let me just... Oh, sorry. So for this case, we would use, yes, we would use u substitution, but not integration by parts, because we only have one function here, right? So we would try, let's try first to use u substitution, which is a method that we do know works, right? So let's try that. So if we use u, we substitute u ln x by u, we have now that du is just 1 over x dx, right? So now that we have that, then bringing it back to the question, we would have sine of u, right? Sorry, sine of u multiplied by dx, which is just x du. But now remember that since u is equal to ln x, that would mean that x is equal to e to the u. So this would be simplified further to be e to the u times sine of u du. Now we have two functions, right? So we have the function, the exponential and the trigonometric function. So with that in mind, if we were to use integration by parts now to continue here, what would be, I'll call it A just so it doesn't confuse with the other U here. What would be our A and what would be our DB? Which is just another name for our DV. Suggestions? If we keep in mind the logic that we're using, that we choose A in this case to be the function that is easily differentiable, right? Both of these functions, as you can see, we have two functions, e to the u and sine u. Both of these functions, as you can see, are easily differentiable. So now the choice becomes which one is A and which one is dB. So what do you think?
I think we should make A to be equal to sine u.
Okay, that's one way. Yeah, let's try that.
Yeah.
Let's try that. So if we let A be equal to sine u, Then our dB will just be e to the u du, right? And our dA will be cos u du, right? So now that we have that, using that logic of integration by parts, we have a minus b multiplied by, multiplied by b dA, right? So if our dB is e to the u, our b is just e to the u. Remember, the integral of e to the u is just e to the u. So that means that our a times b will just be e to the u times sine of u minus the integral of e to the u, right, b, multiplied by dA, which is cos of u du. So now we have to evaluate this integral separately. So let's evaluate it. E to the u cos u du. Obviously, as you can see, there's a pattern here, right? We have e to the u, before we had e to the u sine u, now we have e to the u cos u. And for those who were here in our session last week, I was saying that when you have cases like this, where you have to do you have to do integration by parts twice for the same, under the same question, it's always recommended to stay consistent. And what I mean by that is, before we let our a be equal to sine u, it means that for the second integral here, we'll also let our a, right? I'll still use a because it doesn't make a conflict there. We'll still let our a be equal to now cos u, right? So our a will remain the trigonometric function, and our dB will be the exponential. So our dB will remain e to the u du, right? Okay, so now that we have that, to stay consistent, our dA is now negative sine u du. Our b is e to the u. And therefore, this will be a times b, which is e to the u cos u, minus the integral of b dA, which is, right, zoom in, which is e to the u times negative sine u du. This is equal to e to the u cos u minus, so these two minus will just become positive there, plus e to the u sine u du. Now, let's take this and plug it into that expression there. So, our original expression was, if we bring it back, was the integral of e to the u sine u du. And we found that that was equal to e to the u sine u minus this integral here, which we estimated to be this here. So minus e to the u cos u minus the integral of e to the u sine u du. Now, as you can see, this expression is common here between the two. So let's put them together. So we'll take this expression to the left-hand side of the equality. Then we'll have those two expressions, which are the same, so that would become 2, right, times the integral of e to the u sine u du being equal to e to the u sine u minus e to the u cos u, right? Hopefully you guys are still following me there. So now we can divide by 2 on both sides. We'll have the integral, which is the original one, of e to the u sine u du is just equal to 1/2 multiplied into e to the u sine u minus e to the u cos u. So e to the u cos u. And moving back to the original u substitution, which was u is equal to ln x, and x is just e to the u. So this becomes our original expression, which was sine of ln x dx, is therefore equal to 1/2 times x times ln, or rather, sorry, not ln, sine of ln x minus x times cos of ln x. And this should be the final form of this expression. So, right, so you can double check if we didn't make any mistakes there. Right. Any questions? Anything at all? Suggestions? All right. If there isn't any more questions, then we'll stop it here, and we'll meet again tomorrow. Right?